Hi, welcome back everybody. This will be the first of our 2 lectures about stellar remnants. In this section we're going to talk about white dwarfs and neutron stars, which are the non-black hole degenerate remnants of stars. So some typical credits. And this is an artist's impression of a black hole system. This is the star HDE 226868 in orbit around a black hole. This is known as the Cygnus X1 system. It's one of the first black hole candidates that was really analyzed in detail starting around the late 1960s, and what was found was that there was a very strong X-ray source in the constellation Cygnus. Cygnus X1 means X1, the strongest X-ray source in Cygnus, and when astronomers looked at it with an optical telescope, they found a star there, but the star was not at the exact location of the X-ray source. Instead, there seemed to be a situation where the star was in orbit around something, but the something wasn't there. We're going to have more to say about Cygnus X1 later on, but the star itself is a blue supergiant star. And here's another situation where we have a blue supergiant star, in this case a 70 solar mass one. I think HDE 226868 is something like 25 solar masses, or 20 or 25, and it's being orbited by a 16 solar mass black hole in the triangular galaxy M33. So a real quick classification. So we can break stellar remnants and end-of-life results of stars into a number of different categories. So first off, stars that have initial masses of less than about 8 times the mass of our Sun will end as white dwarfs. That's assuming that they're more than about 0.23 or so times the mass of our Sun. If it's a red dwarf that's between like 0.08 and 0.23 times the mass of our Sun, it's just going to keep fusing hydrogen into helium forever until there's no more of that to happen, and eventually it'll just leave behind a cold helium kind of white dwarf type of thing. Heavier white dwarfs will leave behind helium white dwarfs after casting off their outer layers as red giants, but that's not going to be for many tens of billions of years from now and stuff like that. But anyway, other than that, yeah, stars with less than about 8 times the mass of our Sun, they're going to end their lives as white dwarfs. Now, what about the massive stars? Well, if the star is more than about 9.5 times the mass of our Sun, and up to somewhere between about actually more like 18 to 25 times the mass of our Sun, it's going to explode as a supernova, and it's going to end as a neutron star. It's going to collapse to a neutron star. However, anything between about, say, 2025 to up to about 40 times the mass of our Sun, that's eventually going to become a black hole due to material fallback after the reverse shock from that supernova drives more material onto the neutron star and eventually carries it over something called the Oppenheimer-Volkoff limit and collapses it into a black hole. Now, stars beginning their lives with between about 40 solar masses and 130 solar masses, they're actually going to explode as very powerful supernovae, hypernovae in these cases, and they're going to leave behind black hole remnants. Now, some of these supernovae are on the order of about 100 times as powerful as your typical core collapse supernova that we've been talking about before. Say what gave rise to the Crab Nebula and the Crab Pulsar. So consider something 100 times more powerful than that. Even the Crab Nebula, that star, when it exploded in 1054, that was bright enough to be seen for about like 2 or 3 weeks in broad daylight. Well, then imagine something 100 times more powerful. That's 5 magnitudes brighter. So, really bright indeed. Now, between about 130 and 250 times the mass of our Sun, something really special happens. The core of that star is so hot that the gamma ray photons, we're talking about 4 billion kelvins in terms of the temperature, those gamma ray photons are so energetic that they can actually give rise to a positron-electron pair, as long as they're near enough to something like a proton to allow both conservation of energy and linear momentum. But that's going to be the case in such a dense and energetic core in any case. So those gamma rays are so energetic, they give rise to an electron-positron pair, and this pair instability, it ends up happening throughout the core, makes the entire star unstable, and the whole thing explodes in a spectacular pair instability supernova. These things would be even more powerful than those hypernovae that we're talking about that give black holes. And then beyond 250 solar masses, current research seems to indicate that those are just going to collapse directly down to a black hole without leaving all that much of a remnant other than, say, like a hydrogen-helium envelope that went with the outer part of the star. That's one of those newer results over the past decade, that these 250 plus solar mass stars will actually probably not explode. Before, we thought that maybe they would give rise to an even bigger supernova explosion than a pair instability supernova, but newer research is indicating that we don't generally believe that to be the case anymore. But this is not 100% established, so that's something to keep in mind. Maybe 5 or 10 years from now we'll be realizing that it's more complicated than that, and maybe there are further divisions beyond 250 solar masses. Though in truth, it's very difficult to create a star more than about 150 solar masses anyway, because it turns out that the radiation pressure, the brightness of that star is so big that it actually starts to break apart the star. In fact, you can't form a star from a nebula that is that massive. We have found stars that are that massive before, like R136A1, but those are probably the results of stellar mergers after they originally formed. So, I mentioned that there is some speculation on the exact background on some of those numbers, where the exact cutoff is, but the general trend is still probably the case. By the way, astute students might have noticed that there is a little bit of a gap here. I never mentioned what happens between 8 and 9.5 times the mass of our Sun. Those stars actually do explode as supernovae, but they probably don't leave behind a remnant. That's actually an electron capture supernova. It's a weaker than normal supernova, and those typically, we think, do not leave behind remnants. So I just wanted to mention that as well. Now, I also want to mention magnetars. We're going to have more to say about magnetars later, but magnetars are extremely highly magnetic neutron stars, even more magnetic than a typical neutron star. But we have found magnetars in stellar clusters that have stars up to 50 times the mass of our Sun. Well, why is that weird? Well, remember, all stars in a cluster form at the same time, which means they all have the same age. And I mean, by the same time, yeah, there are uncertainties in terms of the exact time of formation. The more massive ones tend to form a little bit quicker, and the more massive ones also go through their lives quicker. But wait a second, if the more massive stars go through their lives, and in this case explode more quickly than the less massive ones, then what we're implying is, say, wait a second, we have a star with 50 solar masses in this cluster that still hasn't exploded. But on the other hand, we have a magnetar, which is the degenerate remnant of an exploded star. So if they all formed at the same time, with the leeway being that the more massive ones form a little bit faster and go through their lives noticeably faster, that implies that this magnetar must have come from a star that was more massive than 50 solar masses, because that star's already dead. So how do we get around this? There are actually two ways that we could potentially get around this. One is that the 50 solar mass star in that cluster is actually the result of a merger of two lighter stars. Another possibility is that our computer models for what happens with a supernova are not quite right. I did come across a peer-reviewed paper recently that proposes, as a result of computer simulations, that pretty massive stars that with masses in this mass range, when you have the core collapse, you actually end up having a quark-gluon plasma, which is a very special state of matter. And this quark-gluon plasma results in a lot more nuclear fusion than you would otherwise expect. You get a lot of R-process nucleosynthesis, which could, if that's the case, that could potentially explain why we have so many very heavy elements, even though we think that a lot of those probably come from the merger of neutron stars, and neutron star mergers should be relatively rare. But if that's how those heavy stars actually explode, then that could explain that. And also, a 50 solar mass star, if during the core collapse phase you get this quark gluon plasma in the core, then that could eventually give the end result of a neutron star as opposed to a black hole. So that's the other thing to keep in mind. So there's a lot more to explore on this, and hopefully we will have better answers on this in the coming years. So, should also mention that neutron star mass ranges are themselves relatively complicated, and I already mentioned the situation between 8 and 9.5 solar masses that you don't get any remnant at all. Now, back to white dwarfs. White dwarfs are the first of the big degenerate remnants that we want to discuss today. The first one was found in 1862. That was the star Sirius B. In fact, there were indications that there was something going around the star that we call Sirius, which is actually Sirius A, even back in the 1830s and 1840s. Friedrich Bessel, who was one of the first people to really confirm stellar parallax, he noticed that Sirius was kind of wobbling back and forth, and it wasn't in accordance with Earth's motion around the sun. So he realized that, yeah, there's something probably around that star Sirius. Well, it was discovered in 1862. What is this star that was discovered? It turns out it has a mass of just over the mass of the sun. It also has a surface temperature of 25,000 kelvins. That's an easy black body fit. And its luminosity is about 1/40th of our sun's luminosity. Well, you have a mass of the sun, temperature of 25,000 kelvins, but a luminosity of less than 3% of our sun's mass. From that, you can derive its radius. It turns out the radius of this star is 5,846 kilometers. Earth's radius is 6,378 kilometers, just to give you a source of comparison. So there is something weird going on here. We have a very, very dense object. In fact, you realize that the acceleration due to gravity on this thing is very, 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 very high. If you were to drop, say, a wrench from 1 meter high on a white dwarf, it would cause a pretty nasty explosion on the surface once it hits. So, yeah, don't drop wrenches on white dwarfs. Anyway, these things must be very dense. So how is it that these stars are not collapsing by gravity? So going back to our HR diagram, we talked about how in previous discussions that around the end of the life of, say, a star between about half a solar mass or so, well, actually more like about 0.8 solar masses or so, you hit the asymptotic giant branch, and in that asymptotic giant branch, you end up casting off the outer layers. If it's a smaller red dwarf, it might do that in the red giant branch, but in any case, at the end of the day, it ends up leaving behind the core of what had been the star. And that core is what we call the white dwarf. And as this casting off is occurring, that's when the star relatively quickly, over a time scale of tens of thousands of years, actually moves from A to B to C along the HR diagram, leaving eventually white dwarfs in this area. White, because notice the temperature, pretty hot. Dwarfs, because the luminosity is not as hot as you would expect for something that has a temperature of tens of thousands of kelvins. So, low-mass stars never actually get hot enough to burn carbon, so gravity eventually causes the core to continue to collapse until its density becomes 1,000,000 times the density of water. So that type of matter behaves very differently. It's what we call a degenerate state. Now, when we say degenerate state in physics, we're not talking about things like Venezuela or San Francisco or something like that. We're talking about a situation where everything is packed so closely together that all of the electrons must be in the ground state of their atoms. So they cannot go to an excited state. That is a special phase of matter called an electron degenerate phase. So that cannot easily be collapsed further because of the Pauli exclusion principle. Remember the Pauli exclusion principle back from chemistry class with those whole electron shell diagrams? Well, you can't put more than 2 electrons in the same little circle in their orbits. So, and even when you have 2 in there, one of them spin up and one of them is spin down. So you can't have 2 electrons in the exact same quantum state. That is the Pauli exclusion principle. And in fact, incidentally, any particle that obeys that principle is called a fermion. Well, because of this, when you have these very dense stars, these white dwarf stars, the electron degeneracy creates a sort of pressure. Well, I shouldn't say a sort of pressure, a very strong pressure, such that these things are able to resist collapsing. And this works for stars of more than, or white dwarfs of more than about 0.5 or so solar masses, and all the way up to, as we're going to see, 1.44 solar masses. Although something actually special happens a little bit before that we're really going to get into in detail later. Now, that upper limit, the fact that there is going to be an upper limit to this electron degeneracy pressure, that was actually worked out by Subramanian Chandrasekhar starting when he was 19 years old. He was on the boat voyage from India to Trinity College, Cambridge, to begin graduate school at the age of 19. So, I mean, since most of my audience here is high schoolers, just imagine yourselves in 1 or 2 years going off to graduate school and while on the journey doing work that would eventually get you a Nobel Prize in physics. So that's setting the bar high. Now, one of the really interesting properties about degenerate matter, something that we actually discussed back when we were talking about Jupiter and giant planets, is that as you add more mass, the size shrinks. The size shrinks with degenerate matter as you add more mass. So consider our sun. When our sun is done and everything, it's going to leave behind a white dwarf that's probably about half a solar mass. That thing's going to have a diameter of about 1.5 times the diameter of Earth. So it's going to be bigger than Earth. But we already mentioned that Sirius B, which has a mass of 1.02 solar masses, well, its diameter is about 90% of Earth's diameter. So yeah, as you add more mass, the diameter is going to shrink. What that means is that there is going to be a limit. After all, you can't shrink something down to 0 size. So here's a picture of the main star Sirius, along with its itty-bitty cute companion, Sirius B. That's the white dwarf star. Here is another picture of that system. Oh, that's interesting. This is an X-ray light. In X-ray light, the bright thing that you see here is the little bitty white dwarf companion, and the dimmer thing you see here is the brightest star in the evening sky. So that's X-ray science for you. In this case, what's happening is that anytime little material or something falls onto the surface of this white dwarf, it causes reactions which end up emitting X-rays. So that's why you end up getting, that's one of the reasons at least why you end up getting X-rays from the white dwarfs. What about temperature? So white dwarf stars, you know, they're the remnant cores of stars, not the remnant stores of cars, the remnant cores of stars, starting off with less than about 8 solar masses. You might think, well, wait a second, I know the internal temperature of our sun, it's about 16 million kelvins, and when our sun starts the triple alpha process, it's going to be 100 million kelvins. So you'd expect these white dwarfs to start off with temperatures of millions of kelvins. Well, that's not going to last long. I mean, millions of kelvins is going to radiate out a whole lot. In fact, that's part of what ends up helping to shed off the star's outer layers. So when the white dwarf is initially exposed, it has a temperature more like hundreds of thousands of kelvins. And within about 30 million years, it has cooled to about 25,000 kelvins. Now, here's that mass-radius relationship that I mentioned before. And notice that there is a point at which the radius collapses down to 0. Though for a carbon-oxygen white dwarf, which is what we're typically going to be dealing with for a lot of these white dwarfs, we realize now that zero radius limit is actually about 1.44 solar masses. I do want to make that a little bit clear. So, assuming that the star does not collapse down into zero size, eventually it will simply radiate off all of its energy, or at least keep radiating off energy, until its temperature becomes only a little bit higher than the cosmic microwave background radiation. So, exactly where we have the cutoff between a white dwarf and a black dwarf, which is kind of the end result of one of these degenerate white dwarfs after it's become really cold, depends on who you ask. A typical number that I've seen is 5 kelvins. So it turns out that the amount of time for it to go down to about 5 kelvins is on the order of 1 quadrillion years. And it might actually be even more than that, because there are some recent results that indicate that once it starts getting cooler, you end up having various reactions in there that kind of heat it up a little bit, and it might end up being more like 100 quadrillion years, so like 10 to the 17 years. The point is, it's a very long time, so we figure it's at least 10 to the 15 years. And again, if the star has or acquires a mass of 1.44 solar masses, that will end up causing an instability, and that takes it beyond this so-called Chandrasekhar limit. And again, Chandrasekhar was 19 years old when he started working this thing out. White dwarfs are relatively common. After all, the universe has been around for almost 14 billion years, so stars have had a long time to go through their phases and end up shedding off outer layers, exposing their cores. How embarrassing. And white dwarfs are present in reasonable abundance in globular clusters. In fact, here's a white dwarf in a nice cluster of stars right here. And recent observations by the Gaia spacecraft have revealed over 200,000 white dwarfs that show that their temperature profiles actually match the theoretical predictions that the computer simulations and the pen and paper calculations are indicating. So when the stars form, the nuclei are packed so tightly that they're basically a fluid, and the electrons are unbound in kind of a sort of haze. So they're unbound in a way, but they're also degenerate, so you can't end up raising their energy levels if they were to become bound or anything like that. And then, over the next few billion years, the nuclei release heat as they form a sort of crystallized structure, and that results in a slowdown in cooling until that crystallization is complete. So the slowdown in cooling ends up kind of extending its lifetime of being relatively hot. Something to keep in mind is that a white dwarf does not obey the ideal gas law. So that the rate at which they cool is different than what you would expect in this type of matter. Now, we've mentioned this Chandrasekhar limit twice now. What happens if you have a white dwarf star that's, say, 1.3 solar masses, and you start adding material to it? Well, that can definitely happen because most stars are formed in multiple star systems. I mean, more than 50% of the stars in our galaxy are members of multiple star systems. Our sun is special. It's a solo star. So what if it gains enough mass to take it near the Chandrasekhar limit? Well, special things happen during that process. And one of those special things in the meantime is something called a nova. Nova means new star. Here we're talking about astronomy. We're not talking about Northern Virginia, NOVA. So white dwarf stars often have giant companions, and they're going to be gaining mass as these giant companions end up kind of shedding off their outer layers. Think about it this way. If you have two stars orbiting each other, one of them is a 3 solar mass star, one of them is a 2 solar mass star. Oh, actually, let me change my numbers here. Let's make one of them a 5 solar mass star and the other one a 2 solar mass star. Well, that 5 solar mass star, within about 200 million years or so, is going to go through its stages of evolution and cast off its outer layers and leave behind a white dwarf. But meanwhile, that 2 solar mass star is still a main sequence star. The system I have just described is the system of Sirius A and Sirius B. Even though Sirius B is a 1.02 solar mass white dwarf right now, it started off as a 5 solar mass main sequence star. Well, Eventually, as Sirius A, the 2 solar mass star, the one that we see as the brightest star in the night sky, goes through its evolution, it's eventually going to expand and shed off its outer layers. And some of those outer layers will be able to get captured by Sirius B, increasing Sirius B's mass. Now, I should mention that scientists generally do not believe that Sirius B is ever going to end up getting near the Chandrasekhar limit. It's going to gain a little bit of mass, but not all that much. I mean, think about it. That mass that Sirius A is shedding off is going to go into all directions in space. And Sirius B is not all that close to the Chandrasekhar limit. So in situations where they do gain a whole lot of mass, you're talking about a more closely orbiting system, where the white dwarf starts to tidally shred the other star and gains a whole lot of its mass. We don't think that's going to happen with Sirius. But in any case, when a white dwarf gains enough mass that a lot of this hydrogen and helium has accumulated on the surface of the star, eventually you can start a burst of fusion there, basically a helium flash or a hydrogen flash, depending on what's accumulated there. And that can cause the star, the white dwarf that is, to increase in luminosity by tens of thousands of times. We call that a nova. Now, these novae can repeat. So the white dwarf, after it's gained enough mass to start that nuclear fusion on the outer shell again, eventually that hydrogen, let's pretend that it's helium for the sake of argument and that it's a carbon white dwarf, eventually that helium fuses into carbon and all the helium's gone. No more fusion. Bye-bye. Well, the same process that led it to erupt in that nova to begin with can also repeat. It can gain even more mass from its companion and erupt again and gain even more mass. And then, eventually, in some systems, it can accumulate too much mass, taking it near a highly unstable point. Here's a diagram of how this mass transfer kind of works. There's something called the Roche lobe of an orbiting system. The Roche lobe is given by this this yellow dashed line, and if material goes outside of this yellow dashed curve, it can be drawn off into the other object and be pulled in. We've talked about that name Roche before when discussing the rings of Saturn, so hopefully something sounds familiar with that. We're talking about the effects of tidal forces again. Now, it turns out that no white dwarf will ever get up to 1.44 solar masses. There's a very good reason for that. It turns out that, remember that as you add more material to the object, its size shrinks if it's an electron degenerate object. The reason this happens, and the reason this is so important for a white dwarf star, is because of effects of general relativity. We're going to have more to say about general relativity next time. But in general relativity, pressure is actually a type of energy. For those of you familiar with general relativity, pressure is the T00 term in Einstein's stress energy tensor. But in any case, pressure is a type of energy. And this is something that is it's going to result in an increase in the gravitational pull. Anything that has mass or energy results in gravity. That's the whole point about general relativity. Whether it's mass or energy, it can cause a gravitational influence on the environs. It's going to curve space-time around it. Curved space-time is what we call gravity. Well, pressure is a type of energy. And as such, as that pressure increases due to this increased mass, it's going to result in an increased gravitational pull, causing so you pour a little bit of material onto your white dwarf star. It's going to cause a small correction in its mass, which is going to cause a small correction in its pressure. And that small correction in its pressure gives increased energy, which results in increased gravity, which causes the thing to have a small correction in its radius and becomes a little bit smaller. Well, that itself results in another correction, etc., until all these correction terms work out and the star has shrunk. Now, it doesn't shrink all the way down because each of the correction terms is smaller than the one before, until you get close to the Chandrasekhar limit. At 1.38 solar masses, the star has become so small and so dense, and that pressure has become so enormous that you can actually start fusing carbon-12 plus carbon-12. And that results in an instability, because you're talking about something here that is so dense, suddenly starting nuclear fusion here, it causes an instability that travels throughout the rest of the star. That is called the carbon flash. That instability is the sudden ignition of carbon, and it results in an ignition of carbon that travels pretty much throughout the star from the core outward, and you end up getting the whole star exploding. That is what we call a type 1a supernova. It's an incredible explosion. It's about 10 times brighter or so than your typical core collapse supernova of, say, like a 15 solar mass star. So yeah, most core collapse supernovae are the type 2 supernovae. We've mentioned those before. There are also type 1b and type 1c supernovae. These are also core collapse supernovae, but we call them type 1b in the case, or type 1c, depending on the presence or absence of helium lines in the spectra. And whereas type 2 supernovae have hydrogen lines in the spectra, but type 1a supernovae have carbon lines in the spectra. So you might think they should be called type 1c for carbon, but anyway. So type 1a supernovae are these white dwarf supernovae, and they are incredible events. Now, here's the thing. Back with core collapse supernovae, you expect, remember, a lot of neutrinos to be produced, because you have all of these protons and electrons suddenly smashing together as the core collapses. But in a type 1a supernova, the core is not collapsing. The whole white dwarf is literally exploding. Well, because of that explosion and the fact that it's not a collapse, you don't expect all that much in the way of neutrinos from a type 1a supernova. That's one of the big differences between a white dwarf supernova and a core collapse supernova. Lack of a neutrino flash several hours ahead of time, whereas in a core collapse supernova you get a neutrino flash or a neutrino burst several hours before you actually see the star erupt. So I should also mention something like a little rumor out there that you might hear if you're hanging around on bad street corners or something. People might whisper that a type 1a supernova occurs when a white dwarf is collapsing after pulling in enough mass to reach the Chandrasekhar limit. If it reached the Chandrasekhar limit, then it actually would collapse and you'd get a neutron star. But that's not what happens here. You don't get a remnant from a type 1a supernova. You don't get a neutron star, you don't get a quark star or anything exotic, and you don't get a black hole. Instead, the whole thing ends up simply exploding. Now, the Chandrasekhar limit is important, as I mentioned, but it's not important of like, oh, I'm going to cross the Chandrasekhar limit. Remember, it's important because that's the situation where as you gain more and more mass, the size of the thing starts to go towards zero. But as I mentioned, once the white dwarf itself becomes small enough, the pressure and the density ends up being enough such that you can start the carbon flash, and boom, there's your type 1a supernova. It happens at 1.38 solar masses. So there's that remark that I already made about the fact that pressure is a type of energy, and it's that causes the decreased radius as you start piling more material onto a white dwarf. Now, have we observed white dwarf supernovae before? Well, one of the first ones of which we have relatively good records is the one that made Tycho Brahe famous. That was the one in 1572 that he observed. He simply called it a nova, but eventually we found other things that we called novas, and we realized that what he found was much brighter than those other things that we were calling novas. So he actually saw a supernova. It turned out a type 1a supernova. It was very bright, and over the course of months, it eventually faded from view. And the remnants are shown here. This is shown on just a back. The picture right here of the remnant itself is from the Chandra X-ray Observatory. The background is an optical image, so the X-ray picture was just superimposed on the background. But there is evidence that this thing had a companion. A red giant companion, but we're really not sure. We have seen a companion kind of racing away, or at least a red giant racing away from that spot, but Whether that was the red giant that was the companion of Tycho's star, we really do not know. So I mention this because there is a big fist fight going on in the astrophysical community about whether these Type 1a supernovae happen by the mechanism that I've gone through great detail to describe here, or whether it's just the merger of two white dwarf stars. So we're going to come back to that. But anyway, due to the carbon flash, stars exploding by Type 1a supernovae do not leave behind remnants, generally speaking. Sometimes half of the thing might end up exploding due to various instabilities involving rotation and probably magnetic field and stuff like that, and the other half is shot out. We have seen a few of those, but those are rare. Generally speaking, the whole thing goes off, there's nothing left, and it's a really awesome explosion. Okay, so I already mentioned that there's more than one possible physical mechanism for a white dwarf supernova. The dominant method is the accretion of mass past 1.38 solar masses, initiating the carbon flash. But another model is the merger of two white dwarf stars. Whether it's mainly mergers or whether it's mainly mass accretion from a giant companion that's become a red giant is still in the debating stages. I think most astronomers figure that most white dwarf supernovae are due to mass accretion from a giant companion. But there are a lot of people out there who believe that most white dwarf supernovae are the result of the merger of two white dwarf stars. So there's probably some of both. We have fairly decent evidence that certain supernova have been the result of white dwarf mergers, for example. So what some of you might be thinking is that if there are multiple methods by which we get white dwarf supernovae, this could potentially pose a problem for calibrating distances to very distant objects in the universe. So you might remember back when we discussed the cosmological distance scale, the cosmic distance ladder, that we figure out distances to Cepheid variables nowadays based on trigonometric parallax. In other words, we're actually able to directly measure distances to those using the Gaia spacecraft. And upon getting a very precise functional relationship between the period of a Cepheid variable and its luminosity, we can then use those yardsticks, so to speak, to figure out distances to other galaxies. For example, you see a galaxy in the Virgo cluster that's 55 million light years away, and you see Cepheid variables in it, and based on the apparent brightness of those Cepheids and what you know to be their actual brightness based on the period of their brightness fluctuations, you can figure out the distance to that galaxy. Well, now that you have the distances to a bunch of galaxies calibrated using Cepheid variables, you can then look for other, even brighter things in those galaxies. And that's where the Type 1a supernovae came in that we discussed when we discussed them before on the cosmic distance ladder. Type 1a supernovae have the same brightness because they always explode with the same amount of fuel. You have 1.38 solar masses of carbon-oxygen fuel that's going to go into powering that explosion. So because of that, they all have the same brightness, and because you know what their brightness is, because you've calibrated it using your Cepheid variables, you can then use those to figure out distances to galaxies across the visible universe. You can use Type 1a supernovae to figure out distances to galaxies that are about 10 billion light years away. Except for now we realize that they don't all have the same brightness, because some of these things do form by mass accretion from a red giant binary, or companion, and those explode at 1.38 solar masses, but ones that collide with each other, that could have a total amount of fuel of anything, pretty much. Anything over of 1.38 solar masses or more. So that presents a problem here. Luckily, it turns out it's not as much of a problem as you might think, because in spite of the fact that they do have different amounts of masses going in, well, it turns out it's easy to figure out the relationship between the luminosity that it had and how long it takes for that brightness to decay, because that's one of those other things that we've been able to calibrate using Cepheid variables and other distance calibration techniques to galaxies within, say, like 100 million light years of us. So because of that, based on how long it takes the light curve to decay, in other words, the time constant, so to speak, that allows you to determine the peak luminosity. So in other words, here we have another technique of knowing the actual luminosity of the thing. And now that you know the peak luminosity based on how bright it looked in your telescope and based on calibrating for any dust that might be along the line of sight and stuff like that, and after correcting for the cosmological time stretch factor, which we'll talk about when we discuss cosmology, you can figure out how far away that galaxy is. It's a really cool thing. And upon doing this, astronomers figured out that the expansion of the universe is accelerating. We're going to have more to say about that when we discuss cosmology, but it was the study of type 1a supernovae that led to the biggest discovery in cosmology since about 1920. That discovery was made in the late 1990s. So now that we have discussed white dwarfs and white dwarf supernovae, we're going to turn our attention to neutron stars. These are the end results of stars that began with more than about 9.5 times the mass of our sun, but less than about 18 or 20 or so times the mass of our sun. So the end result at the end of the day is that you get neutron stars out of those. So, how did we figure this out? Well, first of all, they were predicted by theory back in the 1930s. It was a result of a calculation by Fritz Zwicky and Walter Baade, but nobody really listened to them. I mean, Fritz Zwicky, his nickname was Crazy Fritz because he had all these outlandish theories. A lot of them turned out to be right. He actually theorized dark matter back when nobody believed in that as well back in the 1930s. But he did other crazy things as well. Like he was very caustic, I guess, with his colleagues, and they were in return not very nice to him. In fact, he called his colleagues spherical bastards because, quote, they're bastards any way you look at them. Another cool story about Fritz Zwicky is that his way of dealing with the twinkling, the seeing effects of air turbulence, he would have a graduate student take a high caliber rifle and fire at his target in the hopes of getting all of the air molecules aligned in one direction. I'm not sure how successful that was, but that was at least his idea. But anyway, Fritz Zwicky proposed that massive stars could end their lives as neutron stars. Nobody paid attention. Meanwhile, in the 1960s, some weird things were found. So, what kind of weird things are we talking about here? So, just a quick introduction. These neutron stars have, at least the ones that have been discovered so far, have masses between 1.2 and 2 times the mass of our sun. They're about 20 kilometers in diameter. In fact, I'll mention they're between like 19 and like 22 kilometers in diameter, something like that. They are the densest objects known. The surfaces of these things have densities of 10 to the 14 grams per cubic centimeter. That is 10 to the 11 kilograms per cubic meter. Now, let's see now. What can we get out of that? We can do some quick calculations. Remember Newton's law of universal gravitation? Of course you do. Force of gravity is between two massive objects is big G, Newton's constant, times the product of the masses divided by the square of the separation distance. Well, from that you can determine the acceleration due to gravity from one massive object. In other words, just divide by the other mass. So the acceleration due to gravity would be big G times the mass of the massive object divided by the square of your distance from it. Okay, well, big G, we're going to round that to 7 times 10 to the minus 11. Yeah, I know it's 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared, or meters cubed per kilogram second squared, whatever, times the mass. Well, how about a sugar cube worth of neutron star material? A sugar cube is about 1 cubic centimeter, and that 1 cubic centimeter is going to be 10 to the 14 grams. Well, that's 10 to the 11 kilograms. So 10 to the 14 grams, that's 10 to the 11 kilograms. By the way, I misconverted. 10 to the 14 grams per cubic centimeter is 10 to the 17 kilograms per cubic meter. But anyway, 1 cubic centimeter of this thing has a mass of 10 to the 14 grams. That's 10 to the 11 kilograms. Well, 10 to the 11 kilograms. Let's put this thing at arm's length. So 10 to the 11 kilograms times Newton's big G, which is about 7 times 10 to the minus 11. So the 10 to the 11 parts cancel. So you're left with 7. At arm's length, we're saying that you're 1 meter away. So that means the acceleration due to gravity of a sugar cube of neutron star material 1 meter away at arm's length is 7 meters per square second. That's a relatively strong pull. You're going to have to brace yourself against that pull, and you'll risk falling down if you brace yourself on something that doesn't have pretty high friction. So that's pretty substantial. What if you reached out to it and tried to touch it? Well, you try to touch it. Your finger is, well, let's say that before you touch it, your finger is like 1 half side length away from this thing. So we're saying that it's about a centimeter away from the center of this thing. Well, a centimeter, that's 0.01 meters. We need to divide that 7 meters per square second thing by 0.01 squared. 0.01 squared is 0.0001. That is 1 over 10,000. That's 1 over 10,000. So we're dividing by 1 over 10,000. In other words, we're multiplying our acceleration due to gravity by 10,000. So the acceleration due to gravity, once you get 1 centimeter away from the center of this thing, as you try to touch it, becomes 70,000 meters per square second. I'm sorry, but that's going to rip your arm off. That would ruin your day trying to touch that neutron star. Your arm would get ripped off, and the force of doing this would end up pulling you toward it. You would end up getting shredded, and you would be destroyed. That would be a bad thing. So don't try to touch neutron star material. Anyway, that just goes to show you how dense these things are. So theoretically, the maximum mass these things can possibly have is about 2.9 times the mass of the sun if it's rotating at the maximal possible rate that it can in order to not shred itself and throw itself apart as it's rotating. But a non-rotating neutron star has a maximum mass of about 2.4 solar masses. But thus far, we haven't found any more than about 2 times the mass of the sun. And I have seen some recent estimates that are putting this upper limit at closer to about 2.2 solar masses. So, yeah, just like with some things with end results of stars, the maximum mass of a neutron star, which I should mention is called the Oppenheimer-Volkoff limit, is one of those things that's still being worked out. It's obviously more than 2 times the mass of the sun because we found these things at 2 times the mass of the sun, but it's not much more. The first object called a pulsar was discovered in 1967. It was discovered by Jocelyn Bell. She was a graduate student under Dr. Anthony Hewish, and they were using radio telescopes to search for rapid variations in radio signals, and they left them running overnight and found one particular radio signal that had a very regular period of about 1.33727 seconds. And eventually they found more radio sources, and they called them pulsars. They didn't know exactly what they were. Originally, the code names for the first one they found was LGM1, meaning Little Green Men 1, like maybe this is an alien signal, though I'm sure that was at least partially in jest. But one of the early ideas on these things is that maybe these are stars that are rapid, like very rapid variables. They're pulsing in, out, in, out, in, out, in, out, in, out. That was realized not to be possible, because some of these things were pulsating very rapidly. One of the very early ones they found was something called the Crab Pulsar, which pulsates 30 times per second. That's not going to happen with a star. I'm sorry. It's not going to be able to give signals that are that strong 30 times per second. You're dealing with something that is much smaller, much more energetic per unit area than something like a normal star. I should mention, in 1974, Anthony Hewish won the Nobel Prize in Physics for this discovery, even though Jocelyn Bell did all the work. As a result, he's often viewed with contempt by the science community for claiming credit, but in truth, it was Hewish who devised the initial experiment and procured the equipment, and basically Jocelyn Bell was pretty much doing what she told him to do, though she did discover the result and eventually interpreted it. So how do we interpret this result correctly? What we realize is that a pulsar is actually one of these neutron stars that Fritz Zwicky and Walter Baade proposed back in 1934. And it's a rotating neutron star. One of the early ones that they discovered was the Crab Pulsar. It's actually at the center of something called the Crab Nebula, the first object in Charles Messier's catalog of fuzzy things that aren't comets, M1. No, this is not Jocelyn Bell. Since you watched the movie Contact in class, you should recognize what this is. But anyway, these pulses are very short signals each time. They have a very thin width when you graph intensity versus time. We found a number of pulsars now. There's one in the Vela supernova remnant. This was the remnant of a massive star that exploded somewhere between about 11,000 and 12,000 years ago. And this thing has a rotation period of 89 milliseconds. That is 11 times per second. So again, you're talking about something more massive than the sun, 20 kilometers in diameter, that's spinning around 11 times per second. Here's a picture of that supernova remnant taken with the Chandra X-ray Observatory. So notice that the spin is kind of giving this nice whirlpool-like structure. That's because these things have very powerful magnetic fields, and it's actually the combination of the spin and the magnetic field that ends up giving energy into this gas and actually taking energy away from the pulsar, the neutron star itself. The Crab Nebula pulsar, that spins 30 times per second. It's seen both in visible light and in X-rays. In fact, the energy that this thing still puts out as a result of its magnetic field and everything that ends up powering the Crab Nebula is equivalent to quite a number of solar luminosities. The fastest known pulsar, though, has a period of just over 1 millisecond. In fact, there are a number of these things that have periods of on the order of a few milliseconds. We call them millisecond pulsars. So in this case, that means this thing is spinning 716 times per second. Again, something more massive than the sun, spinning over 700 times per second. In fact, that's about 1/7 the speed of light at the equator of that thing. Now, we realize now that these things are rapidly rotating neutron stars. And the rapid spin that they have is a result of conservation of angular momentum. And we're going to get to that in just a little bit. But the radio emission is due to protons and electrons being caught in the massive magnetic field and then focused onto the star itself in what we call a hot spot. Now, again, the star is rotating, but again, I mentioned it has a very strong magnetic field. The location of the hot spot is being focused by the magnetic field, but the magnetic axis does not correspond to the rotation axis. Remember, that's the case with most of the planets as well. So in this depiction, we have the spin axis, the axis of rotation, being vertical, but in this depiction, we have the magnetic axis being tilted with respect to that. In the case of Earth, its magnetic axis is tilted by like 8 or 9 degrees from the rotation axis, something like that, and that's constantly changing in any case. So let's consider another situation with less resolution, where you have the magnetic axis being perpendicular to the rotation axis. Well, due to this collimation of these charged particles by the magnetic field onto this hot spot on the surface of the star, that ends up sending out a beam, a jet, in opposite directions, one emanating from each side where the magnetic field ends up going into or out of the object. Well, these jets end up swinging around because, remember, the thing is rotating really fast. Well, if the beam of these jets happens to cross Earth, we see a blip. We see a blip, and we see a blip every time that happens. It turns out that these things are extremely precise extremely precise clocks. They're more precise timekeepers than any of the atomic clocks that we had until relatively recently. Now, as I mentioned, the Crab Pulsar emits lots and lots of energy. It's actually about 100,000 solar luminosities. So the energy itself comes mainly from the rotation of the pulsar, and there's also some coming from the spinning magnetic field of the pulsar. But if you just look in terms of the rotation of the pulsar and the fact that in the case of the Crab Nebula, that rotation is slowing down due to its interaction with this matter. The rate at which it's slowing down matches the amount of energy that's emerging from the Crab Nebula. So think about it this way. First, on day 1, the Crab Pulsar is rotating at, say, a certain rate. At day 2, it's rotating at a slightly slower rate. Well, that means that on day 2, it has a slightly smaller rotational kinetic energy than it had on day 1. Well, that difference in rotational kinetic energy is what must have gone out into the nebula. So if you divide that difference in energy by the time, in this case I said 1 day, that's the power that is being radiated off, and it turns out that is 100,000 solar luminosities. Here's a picture of the Crab Nebula taken with, I think, the Hubble Space Telescope in this case. And this is a zoomed in picture with X-ray light, and again you see that really cool swirl. The pulsar itself is this star right here. This right here is the pulsar itself. It's the kind of rightmost star of these two bright stars kind of near the center of this swirl. So you might wonder, well, why isn't it right here? Again, kind of think a little bit in 3 dimensions right here. There's really also something coming down right over here, so you're looking at the center of a globe right here. And again, we're just seeing that projected onto our 2-dimensional photograph. Now, what's the composition of neutron stars? Despite popular belief, they are not composed entirely of neutrons. In fact, we now recognize that the outer shell, the crust, contains electrons, ions, especially like iron nuclei, stuff like that. And then there's an interior that's a neutron superfluid, which is a frictionless state of matter. And then at the very center, we think, a quark-gluon plasma. Yeah, I mentioned that quark-gluon plasma before with regarding the supernovae. That is something that we actually are thinking more and more is important. And if that's the case, then we might be able to get a whole lot of the heavy elements from core collapse supernovae after all, as opposed to from emerging neutron stars. We're going to talk about that soon. Magnetic fields of neutron stars. They are very, very powerful. I'm going to go through kind of the rest of this relatively quickly, but so that we can start talking about gravitational radiation and gravitational waves. But if you need to pause the video to look at it in more detail, then definitely do so. Typical magnetic field strengths for neutron stars are about 100 million Tesla. Again, Earth's magnetic field is about 0.00006 Tesla. That is 6 times 10 to the minus 5th Tesla. So these are extremely strong magnetic fields. And again, they rotate really fast. There are a whole bunch of them in our galaxy. We figure there might be about 100 million neutron stars in our galaxy. We've only discovered about 2,000 so far, though. Why do these things spin so fast? I already mentioned it's because of conservation of angular momentum. What does that mean? Well, if you have a star, that star is going to have anything that's a solid body, or even a particle rotating about some axis, especially if it's not its own axis, is going to have something called a moment of inertia that's not equal to 0. In the case of a sphere, that moment of inertia is 2/5 mr squared. What I really want to get at is that this moment of inertia is equal to some number times the object's mass times its radius squared. The angular momentum is equal to that moment of inertia times the rate at which it is spinning, the angular velocity omega. What does that mean? As the star shrinks, remember the core is collapsing here. The neutron star is the collapsed core, talking about something that started off like the size of our sun, collapsing all the way down to the size of a city. That collapsed core has shrunk by a large amount. So the radius has shrunk by a large number here, and you're squaring that. What that means is that this omega must become larger to compensate for the fact that this r squared is getting smaller. So the angular momentum needs to be constant. That's a law of nature. During an interaction, the angular momentum before the interaction, total angular momentum of the system before the interaction, is equal to the total after the interaction. So as the object gets smaller, it must be starting to spin faster. That's just like the classic case of an ice skater pulling in the arms and spinning faster upon doing so. Why are the magnetic fields so strong? It's because of another conservation law. It turns out that for a collapsing object, a conserved quantity is magnetic field strength times radius squared. So as the object gets smaller, the magnetic field is going to get much larger. There are special neutron stars called magnetars. Magnetars are neutron stars that have magnetic field strengths on the order of 10 to the 11 Tesla. That's about 1,000 times larger than the field strength even of a normal neutron star. This 10 to the 11 Tesla, that's kind of more like a maximum number. They tend to range, I think, from about 1 billion Tesla to 100 billion Tesla. But in any case, it's an extremely strong magnetic field. If you put one of these things in place of our sun in the solar system, all of the credit card strips and all of the magnetic credit card strips and all of the hard drives, all the way out to the distance of Pluto, would be wiped clean. There would be, all the information would be scrambled due to this incredibly strong magnetic field. So that's a really amazing thing with these magnetars. How do magnetars occur? It's actually because of an instability that occurs during the initial core collapse. So as this magnetic field is increasing really rapidly as the core is collapsing, this actually, in terms of the interaction with the very high temperature and the very fast rotation, ends up introducing what we call a magnetic dynamo, and that actually significantly increases the magnetic field strength as this thing continues to collapse. It doesn't happen with all neutron stars, but it happens with the ones that end up becoming magnetars, and that ends up giving it a much stronger magnetic field. But remember, there's energy in that. Where did that energy come from? It was from a conversion during this collapse of rotational kinetic energy into the magnetic energy. So magnetars actually spin much slower than your typical normal neutron stars. So they might spin like once a second or something like that. Now, just because it's spinning once a second doesn't mean it's a magnetar. Remember, these things get slower in their spinning due to the interactions with the supernova remnant itself. So that's something else to keep in mind. So here is kind of inside of a magnetar, and again, this inner core we think is probably a quark gluon plasma. That's the current state of the research right now. This is an image of a magnetar taken with an X-ray telescope, the XMM Newton telescope, with the colors just indicating the various energies and everything, and there's kind of your supernova, the rest of your supernova remnant. Very energetic environment here. Magnetars have been implicated in a phenomenon called long-duration gamma ray bursts. These are bursts of gamma rays coming from other galaxies. There are lots of different types of gamma ray bursts. We're going to talk about some of these in more detail when we talk about black holes, because some of these things are incredibly, incredibly bright. But in fact, in the case of one gamma ray burst that occurred, this was in a galaxy that was something like 8 billion light years away, and for a brief period of time, it actually had an apparent magnitude of about +5, which was bright enough to be seen in the night sky with the unaided eye. That was the most distant object that has ever, as far as we know, been able to be seen with the unaided eye. But it was only like that for a few seconds, so if you missed it, too bad, so sad. You'll have to wait another 100 years or something. But anyway, these things fade very quickly from brightness, but some can last for hours, especially in terms of their gamma ray emission. And magnetars are responsible for some of these things. They're also responsible for another repeating event called soft gamma repeaters, low energy bursts of gamma rays that come in a relatively regular cycle. But yeah, these long duration gamma ray bursts occur when you have something like a magnetar at the core of an exploded star that is providing lots of energy as it draws in material into its magnetic field and powering that into jets, and those jets end up happening to, the line of sight from those jets might happen to be along that of Earth. So here's an artist's reconstruction of a magnetar, of a gamma ray burst being powered by a magnetar during the formation of this after the collapse of this massive, what had been a massive star there. Now, moving on to gravitational waves. Some neutron stars occur in binary systems. That actually shouldn't be all that surprising, because generally speaking, you get very massive stars when you have very dense areas in giant molecular clouds. So when you have these binary systems, they can eventually merge together. So you can also have like mass transfer from, say, like a neutron star with a giant companion. But what about, say, like a neutron star and another neutron star? That's where things get really exciting. that's where we're talking about gravitational radiation. So electromagnetism, we've discussed it early on in the course, predicts that any accelerating charged particle will lose energy by radiating photons. Well, it turns out any accelerating massive particle, as long as it accelerates in certain ways, will lose energy by radiating what we call gravitons. Now, I should mention that this will not occur due to, say, like a pulsating variable star. When you have a spherically symmetric acceleration in the parts, all of the effects there end up canceling. In fact, even if it ended up pulsing outward along one axis and inward on another axis, you still might not get that, because it turns out if it's symmetric along a line, you're also not going to get this gravitational radiation. But in a lot of other types of explosions, you're not going to have those special symmetries, or I shouldn't say explosions, but interactions. You're not going to have those special symmetries, and you're going to end up getting gravitational radiation. Well, that's a loss of energy of the system. That energy goes out into space. The objects that we're concerned about in the system end up losing a little bit of energy, orbital energy. That means that they end up getting closer to each other, which means that they're going to end up orbiting each other even faster and radiating off more of this gravitational radiation until they eventually merge together. And that final burst before the merge can end up producing lots of gravitational radiation. This can happen with two neutron stars orbiting around each other. This can also happen with two black holes orbiting around each other. In the case of neutron stars orbiting around each other, with these situations where they're merging, getting closer and closer together, they're going to orbit a lot of gravitational radiation. I should mention really quickly, though, a rotating object will also slow down due to gravitational radiation, but that's a noticeably slower process. The radiation of orbital decay is orders of magnitude stronger than that of rotation. So I'm actually going to move on from the rotation bit. Now, here is a picture of, here's a graph of the period versus time for the Vela pulsar. And in this case, notice that over time, the rotation period ends up getting slightly longer. Now, it's slightly longer, so notice that over the course of like 10 days, we end up going up by only about 0.0001 milliseconds. So less than a millionth of a second over a period of 10 days. That's mainly actually due to interaction with between the magnetic field and the supernova remnant itself, but a small part of that actually does come from the gravitational radiation. Now, there is a gap here. That's actually something called a glitch. A glitch occurs when a neutron star ends up kind of reorganizing its crust. It's basically like a star quake, and it becomes slightly smaller, and since it becomes slightly smaller, it's going to be rotating a little bit faster. So that's when that period suddenly decreased there. Anyway, two neutron stars orbiting each other will also have a decay in their orbits. That's something that has macroscopic predictions. In other words, you can make predictions of that from Einstein's field equations and measure those over the course of a human lifetime. The first time this happened was the famous Hulse-Taylor system. This was measured in the late 1970s, and they ended up getting a Nobel Prize in physics for their efforts in the early 1990s. But their measurement showed that the predictions of general relativity were correct to within 2 parts per trillion. So it's a very, very precise agreement between measurement and theory. In other words, general relativity is right. Other theories of gravity that we know about that aren't consistent with general relativity are wrong. What about gravitational waves? We mentioned that these things are emitted, but have the waves themselves been detected? I mean, here with the Hulse-Taylor pulsar, you're detecting the effects of gravitational radiation, but you're not directly detecting the waves. You are observing, using the electromagnetic spectrum in your observations, the result of this. What about the waves themselves? These were found in 2016, or actually they were found in 2015. The result was announced in 2016. In this case, it was a merger of two black holes, each with masses on the order of like a few dozen times the mass of our sun. We think it was in a galaxy about 1.3 billion light years away, but this was an amazing event when this happened. So how did this work? The LIGO detector was the experiment that was actually first formed with the big goal of detecting gravitational radiation. The typical diagram for it is you have a light source that ends up going into a beam splitter, which is basically something like a half silvered mirror. Half of the beam ends up going through, half of it ends up getting reflected at 90 degrees, and you have a mirror. And then you have this mirror that reflects off the mirror, goes back through the beam splitter, and the part that went through the beam splitter also reflects off of another mirror and reflects over to here to where you have your detector. Well, here's the thing. What you do is you can very precisely align things until these two different beams are either completely in phase or completely out of phase. So if they're completely in phase, you're going to get a signal at your detector. If they're completely out of phase, you're not going to get a signal at your detector. In truth, it actually reflects a whole bunch of times, increasing the thing itself is something like 4 kilometers long, but you reflect it a whole bunch of times until the overall path length is like hundreds of kilometers or so. But in any case, when a gravitational wave goes by, that slightly changes the length in this mirror. And by slightly changing it, it ends up making these signals very slightly out of phase. And as a result, you know that there was a gravitational wave there. Now, there are multiple LIGO detectors to make sure that you're not just dealing with some blip due to some local phenomenon like a pig running around a barn or something like that. But in any case, these provide another means for exploring cosmic phenomena. We have discovered a number of these things over the past like 5 years, so lots of gravitational wave observations. The point, though, is they go beyond the electromagnetic spectrum. You're using a completely different method of observing astrophysical processes. And a great example of this was the so-called kilonova of August 2017. So right as we were celebrating the nice North American eclipse that I got to see when it was a total solar eclipse on August 21st of that year, there was another observation in the astronomical community. In October, they announced the discovery that had been made back in August of a significant gravitational wave signal from a location in space that precisely matched the observation of what we call a kilonova in the galaxy NGC 4993. So a kilonova it's a term used for something that's kind of like a nova but 1,000 times more powerful. It's not as bright as a supernova. Again, it's about 1,000 times more powerful than your typical nova, but it's still pretty bright. I mean, you can see it even though it's in a different galaxy, just using telescopes. So here's a picture of NGC 4993 with the kilonova itself. So it is something you can see. I mean, I said it's not as bright as a typical supernova, but it's not incredibly dimmer either. But this happens from the merger of two neutron stars. Well, here's the thing. We used LIGO to detect the gravitational waves that were emitted from the merger, and we used telescopes to analyze the kilonova itself. That was a really awesome achievement, the fact that we used two completely different methods of observation using absolutely different information media to analyze and study this event. Merging neutron stars are now believed by many people to account for many of the very heavy naturally occurring elements on the periodic table, things like gold and platinum and uranium and stuff like that. But the jury is still out on that, as I've mentioned before. It could be that if the quark-gluon plasma in the center of your forming neutron star is important enough, then you could generate a whole lot of heavy R process elements that way as well. But in any case, yeah, we simultaneously used completely different information media, gravitational radiation and electromagnetic radiation, to observe this kilonova at the same time. That was an awesome achievement. And just the discovery of gravitational waves themselves is an awesome achievement. It is actually one of the greatest achievements in science in history. It's a very, very important achievement, the fact that we were able to detect gravitational waves from the merger of black holes and also merger of other objects like these neutron stars. So, in any case, there are other gravitational wave observatories out there. The Virgo observatories, they're also up and running. We have some recent observations from those as well, and there are also ones like LISA that are coming online soon as well. So anyway, just a real quick thing. Mergers with white dwarf stars, as we've mentioned, can also give you supernova explosions, and also mergers between, say, a white dwarf and a neutron star. You can get a type of supernova explosion that way as well. In fact, that type of explosion can produce most of the universe's calcium, according to a lot of people. Other funny things, if you have a neutron star at the center of a red supergiant star, that could produce a more long-lived star that we call a Thorne-Zitkov object. And we may have found one of these cool things back in 2014. Now, what's next? So, if the core is less than 1.4 solar masses, you're going to get a white dwarf at the end of the star's life. If the core is between 1.4 and 2.9 solar masses, a neutron star is going to remain, even though the original star itself was a lot more massive than that. But what if the core of the star is more than that? So you have a star that initially started off with more than 20-something solar masses. What happens then? Well, that's where we start talking about black holes. We're going to dedicate an entire lecture to this, and I'll see you all next time. Thank you.